All right. So yes, as Motaz mentioned, I will be discussing Starlink operations, kind of what I'm calling a forensic TLE analysis. And so the basic agenda for today is, I'll kind of talk about the current status of the constellation, what I've been able to learn about their ascent to mission orbit, what I've been able to learn about their mission orbit, and then finally I'll kind of get to the billion-dollar question of conjunction analysis. What are they doing about conjunctions between Starlink satellites? I'm not really looking at external conjunctions at all. And a couple of notes. Bottom one first, as per usual with this conference, if you have any questions, please type them in the question sections of the app, and we'll get to them at the end. And then finally, the big note I want to make is that all this data is publicly available, or all the information I've derived comes from publicly available data sources. It mainly comes from the Celestrak supplemental catalog, which those are actually generated from SpaceX EFEMs that SpaceX has given permission for Celestrak to fit and then redistribute TLEs. And an important note about that is because they're derived from the SpaceX EFEMs, Celestrak is also able to provide an RMS value of the TLE fit, which gives a good indicator of the TLE accuracy. So basically, in general, you can kind of have more confidence in these TLEs than say your typical SSN derived TLEs. And I make a couple of mentions of TLE accuracy in a few places within the presentation. So in terms of status, I actually started tracking the data and kind of pulling down and archiving the TLEs all the way back in February, and just kind of have kept an eye on things as time has gone on. And so I've really been able to watch it grow. And I used FreeFlyer to do all of my analysis, including actually downloading the TLEs. A lot of my analysis is actually just a script I run once a day just to pull the data down and do some basic calcs. And one of the things I did was I put together this kind of display of high-level status of the satellites in the mission orbit, kind of neglecting the stuff that has just been launched or is waiting in the parking orbit. And as of February 25th, you can see there were only 3 planes on orbit, only a total of 57 satellites. And a brief outline of this display is that it's color coded by launch. So the first 2 planes in orange were from the first launch of the 1.0 satellites, the desired operational constellation, and then the green is the second launch, and so with each plane, it adds to it. And so if you look at recently, not today, but as of earlier this week, this is where they're at. And so you can see, everybody's heard about the launch schedule and everything, and they've really been pushing like crazy. Their constellation is almost halfway done. They still have a ways to go, but I think they have enough satellites launched at this point to get to halfway, the constellation halfway complete at the 550 altitude by I think roughly by the end of the year. And so you can see, they've launched, they've made a bunch of different launches and color coded accordingly. I used FreeFlyer's new color palette routines and capabilities with 7.6 to handle this. And you'll see later in a lot of my plots, I've actually used the same color palette and the same launch color coding scheme to color my plots. So there's a good consistency between plots and views. One other thing I want to mention about this view is that the RANs are not the raw RANs of each plane. What this is kind of a co-rotating RAN. So plane number 1 is actually the first plane that was put on orbit, and then everything is a delta RAN from the current RAN of that plane number one. So the planes don't move around in this display; they're always kind of there. And an interesting thing relevant to the CA later is that, as of earlier this week, there are 812 different plane crossings in the operational constellation. Plane number 23 is actually ascending to the mission orbit as we speak. It will kind of complete its insertion into its plane slot probably by the end of the day, if not tomorrow. That will bring the number of plane crossings up to 870. And with this approximate number of conjunctions per day, it is very approximate. There's different numbers of satellites in each plane. So it's real hard to kind of pin down an exact number. But I just used kind of an average of 18 satellites per plane. And it's definitely not, there's not that many serious conjunctions. It's just the number of potential plane crossings by satellites per day. So it's very approximate. But it gives a good indicator of kind of, what the potential is for, operational impact. So a little more on current status. Another view that I use is this Apogee and Perigee view, which really just looks at all the TLEs in the catalog, just kind of in order. And so I have the mission orbit of 550 kilometers altitude marked across the top. The light green lines are basically the typical Apogee and Perigee range of space station, since that's a relevant marker. And so you can see, they have most of their current catalog up at the mission orbit. They've launched 900 satellites. There are roughly 829 in the catalog currently. 549 have made the mission orbit. It's probably about 70 right now raising the mission orbit. I think at least 10 or so have made it into plane 23 now. And then there's roughly 180 or so in the parking orbit, which you can see at 380 kilometers across the right side of the plot. And again, this is color coded the same way as the view before. One important distinction is there are a few remaining from the original version 0.9 launch from last year. They've deorbited most of them, but not all of them. And then you can see all these kind of stragglers at various altitudes and TLE indexes. These are all satellites that are in some form of anomalous state. Some of them are still maneuvering, some of them are not. It's hard to say exactly what's going on, but they have had a non-trivial failure rate of at least kind of 1 or 2 satellites per launch have failed. I know 2 from the most recent launch seem to be unmaneuverable because they never kind of transitioned out of their injection and decayed within a few days. Another way to look at the data. So one kind of theme of this, I guess, that I neglected to mention initially is just, with so many satellites, there's just a lot of data. And, really, to do an analysis like this, you have to kind of turn that data into information and knowledge. And so I found that I've just needed to look at the data in many different ways to make heads or tails of it. And so I'm just kind of going through the different ways that I've looked at the data from day to day to kind of get a real feel for what's going on. So nominally, their plan is for 72 planes, and so you can see this is the actual raw RAN of all the satellites. And so as the RAN drifts, they'll kind of twist around this polar plot, but they're indicated, they're labeled with their numbers for their plane number in the constellation, which is completely arbitrary. It's my own numbering convention, but who knows what they're using operationally. but you can see very easily over, at kind of the 3 o'clock hour, you can see as the status as of a few days ago of the plane that is ascending into slot number 23, batch of 19 or 20 satellites right there approaching the mission altitude. You can see the other satellites in groups that are waiting in the parking orbit for their ascent. There's another plane cohort ascending over here, going into the plane number 71 slot. And so they started by just filling in every 20 degrees of RAN. Now they're filling in planes at every 10. Once they've completed that, they'll finally go down to 5. Originally, they had a 350 kilometer parking orbit altitude, but they after multiple launches, they apparently decided to raise it up to 380 kilometers. That gives a RAN drift of about 0.41 degrees per day. So they typically start at about 25 days. They start their ascent from the parking orbit about 25 days before they want to inject. Going back, so this plot, is good for showing the plane deployment and kind of where particular launches and planes are heading as they begin their ascent. But you can't really see anything about the phasing of the satellites within the plane. So a good way to look at that is this, what I call an overview plot. That is really, it's again that co-rotating RAN is the x-axis. So the coloring on this is different. I let this one be inconsistent with the rest, but plane number 1 is the far left, the vertical line of dots, and so the delta RAN is the x-axis, and then the Argumental Latitude is the y-axis, which is a easy and clean way to show their phasing within their orbit. And so at a real quick glance, you can see how big kind of where the constellation is, how big the separations are between the satellites, whether or not the satellites are fully populated. Their original FCC filing was for 22 satellites per plane. As of right now, they're only populating 20, and they're spacing it based on that. So if you see the green line in the center at 160 RAN, you can see they're all evenly spaced, and it's quote unquote fully populated with 20 satellites, and so they're all about 18 degrees apart. But then other planes that have only 18 or 19 satellites, you can see the open gaps that they're missing. And so I don't know if they're going to eventually fill in with 22 once they have all the planes populated with 20. We'll just have to wait and see. I don't have any insight into their operations. But this is a very easy, very static way to kind of get a high level view of what the constellation deployment looks like. And you can see also on this that there are a few that are kind of out of phase. They haven't fully phased out into their slots yet, and I'll get into how they do that in a minute. But generally, what I would say is this isn't it's not an accurate way to really determine how tightly they're keeping in their box or anything like that. But the last thing I will say is that one thing that this view does provide is an interesting insight into another interesting insight into their plane organization. If you look closely, you'll notice that for each plane separated by 10 degrees, they've staggered the Argumental Latitude. They shift by, say 5 or 10 degrees, maybe probably 9 degrees, given that they're 18 degrees apart. I haven't checked in detail, but that's probably what it is. I'm not sure why they've decided to do that. It could either be coverage on the ground or a decision they made for CA. It's hard to say. The planes that are 10 degrees apart in RAN, they'll have their conjunctions at higher latitudes, and there tend to be more conjunctions more plane crossings, I should say, at higher latitudes. So maybe it's driven by that. I don't know. Again, it's speculation because I don't know their operations, but it's very clearly a design decision they made. So to move on a little further, we'll talk about their ascents and how they get into that in-plane phasing. And so what I've done to look at to kind of illustrate their typical ascent plan is I'm showing all 3 ascents from a given launch. Typically, they try to populate 20 satellites into a plane, and so they try to populate 3 planes per launch typically. And so from launch number 8 in earlier this year, um, there were 3 planes that were raised, 3, 7, and 11, and actually went that kind of in reverse numerical order, 11, 7, and then 3. And so what you can see in this plot is the 20 or so that were raised into plane 11. You can see them from their launch injection at their elliptical, very low launch orbit, when they circularized up to their parking orbit. And then for this first cohort, they basically immediately started ascending towards plane 11, towards the slot for plane 11. And you can see their semi-major axis phases out as they ascend, and then they kind of equalize at 550 altitude. And you can see there's actually one kind of outlier that they raised actually above the nominal altitude, and then after say 30 days, 20 or 30 days, dropped it back down in, and you'll be able to see that was associated with in-plane phasing. And so then that's the first plane from the launch. The next plane, you can see they waited about 35 or 40 days at the parking orbit, and then they again started their raising. And this one was kind of a more standard, more nominal launch. The satellites are kind of less phased out, and there weren't any stragglers getting into the operational plane. And then finally, the last plane, took on the order of 160 or so days for the whole ascent. And you can see, again, this one, there were a few kind of outliers in terms of the ascent and the way they handled phasing. You can get a little bit of information from the phasing that way, but I think a more convenient way to look at the data is actually through the mean motion. And so when you plot the mean motion over the ascent from the parking orbit up to the mission orbit, this is plane 7, the middle one that was, as I said, kind of more standard. You can see that basically what they did is at the beginning of the ascent, the spacecraft are all bunched together at essentially the same mean motion, and they kind of stagger their burns, which then kind of phases them out in semi-major axis, and then they do consistent burns through the ascent to allow them to keep consistently different mean motions that in turn allows them to phase out over time. And so you can see that they kept, there's a little bit of wiggle here and there, but they basically kept the delta mean motion consistent all throughout the 25 days or so of the ascent. And the next plot shows you exactly how that bore out. So this is for plane number 7, the argumental latitude over time for the 20 or so satellites, and it starts from injection. So you can see, at injection, all the satellites were just, as per the launches that we've all seen, they're all just kicked off in a chunk. And so they're all at essentially the same argumental latitude. Obviously, there's some differences, but it's very negligible on this plot. And as they raise up to the parking orbit, you can see, when they got to the parking orbit is indicated with the green line, and then the other 2 green lines show the ascent from parking to the mission orbit. And you can see going across time, as they raise to the parking orbit, they let them phase out some. The nominal separation at the parking orbit is about 300 kilometers. And they keep that phasing consistent all throughout the time at the parking orbit. The various locations of kind of the group of argumental latitude is really just driven by the timing of when the TLEs were generated. But you can see there's consistent separation across. And then when you get to the final ascent to the mission orbit, you can see that they start phasing out very quickly based on that delta SMA and subsequent delta mean motion. And they start phasing out. And then once they get onto orbit, you can see that they're mostly spread out there's still some additional phasing that kind of happens with small tweaks to SMA, and then kind of by the end they're in a very regular phasing. And so so basically they don't have to do any sort of significant kind of on ramping or whatever as they get up to the mission orbit. They're essentially ready to go. It makes sense. I mean, that's you might as well take advantage of the ascent time to do that. That's how they get from their parking orbit up to their mission orbit. So is there anything more we can learn about their mission orbit? Of course, the short answer is yes. A lot of the information is already publicly known from FCC filings. 550 kilometers, 53 degrees inclination, 72 planes, and again, their FCC filing was 22 spacecraft, but really they're only doing about 20 so far. But there's not been any information on argument of perigee and eccentricity, and so really it comes down to, are they flying some sort of frozen orbit or not? And for obvious reasons, frozen orbits have some advantages for LEO constellations, especially ones that are looking at the ground or communicating with the ground. So it seemed obvious to me to look at that, and so this is just a snapshot for all the satellites on the mission orbit. You have to kind of ignore the stuff that it's either just been launched or is being raised to the parking orbit, because their eccentricities are going to be much higher and kind of all over the place. But if you look at the operational satellites at the mission orbit, you can see they really cluster them at essentially 0.1 degree eccentricity, 0.001 degree eccentricity, and 85 to 95 degrees argument of perigee. This particular plane had just been kind of initialized recently when I did this plot, and so over time, what I've seen is they'll start with argument of perigee that's kind of off, and it'll drift in as they kind of get it tightened down once they get on orbit. And so that's what it looks like as a snapshot. But argument of perigee and eccentricity will naturally drift over time. So are they kind of forcibly holding that AOP and ECC, or are they letting them drift around? So what I decided to do to look at that was just take a few of those and trend them over time. And so what this plot shows is for one particular satellite in particular, it's 1218. So I took one day, I took basically 185 days worth of TLEs. That's the orange data series. And then I took the first TLE and propagated it using a full fidelity propagator to just see how, without maneuvers and anything else, how does the argument of perigee and eccentricity drift and evolve over time. And there's going to be some error in this in converting from a TLE state to a kind of an SP propagation state. But so I did it for multiple spacecraft to just kind of look, and what you see is kind of varying levels of agreement. Some agree better, some agree worse, but none of them are really, really that close. They're kind of all over the place, and so I could have shown more, but it's kind of more of the same. And so what it seems to say to me is that they are continuing to forcibly control eccentricity and argument of perigee to keep it kind of within that main region that the overall constellation is in most of the time. So that seems to be one indication of kind of regular maneuvering of the constellation. But is there anything else we can determine about the mission orbit and maneuvering? Maneuvering in particular was kind of a curiosity of mine, because it's just with this many satellites and that many plane conjunctions, it seems like they would potentially have to maneuver a lot. So one other thing I decided to look at was essentially their along track separations over time. For one particular plane of spacecraft, of the 19 or 20 satellites, what's the separations between them? And I'm calling it a control box. I don't know that they really have that term. It's probably only driven by the coverage on the ground, so that they can have kind of uniform coverage, and then CA. What do they have to do to get out of the way of each other? And so it seems like they're roughly holding plus or minus 40 kilometers around the nominal separation between the satellites, which would be 2176. And I didn't draw it because it'd be it kind of covered up, but you can see it's essentially right through the middle of this band. And so this band of mess is all the spacecraft separations over a 30-day period. And so each trend line, like this light teal one that's kind of more visible on the top, it's the difference between two satellites over time. And so one would be satellite A, and the satellite ahead and the satellite behind. And there's a couple of things to note about the way I generated this plot. One is, it's over 30 days. And so what I did was I took each day's TLEs and propagated those TLEs over the course of the whole day. So there's data rev to rev over the whole day. And by doing that, it also helps give you an idea of continuity of the TLEs. So as you can see, and the teal band I mentioned, this is roughly a 6, 7, 8 day period. And while there are small discontinuities, it's very, very consistent over that time period, which means that the TLEs were very consistent. And so, because essentially both satellites' TLEs were very consistent, I think it's fairly safe to say that there were no significant maneuvers happening in that 6, 7, 8 day period. But then there's this trend line reversal, around about day 312, where the separation between the two satellites goes from growing back to shrinking. And to me, that is a very, very likely indication of a maneuver of at least one of those two satellites. They don't, that is a trend that, has to be altered by a change in semi-major axis by at least one of the satellites. And so you can see those trend reversals are all over the place. And then furthermore, you can see there are various discontinuities. Some of them I think are, potentially just TLE fit errors, particularly ones that kind of go way off like this. I definitely have confirmed that some of those can be TLE fit errors, but some of them may be maneuvers. Hard to say. The band, the width of the separation line is really just driven by that eccentricity of the orbit. They'll kind of pulse in and out. Their separations will grow or shrink by a couple of kilometers as they go through apoapsis versus periapsis. And so there's a couple of things at a high level that I think we should note about this. One is it appears like they're maneuvering a lot. Back of the envelope guesstimate is it looks like kind of on average about every 3 days. This trend here that I've made mention a couple of times is kind of one of the longer ones I've seen, and it's only 6, 7, 8 days. And you can see a lot of them have much more frequent breaks and changes in their trends. The other thing I'll mention is it's not difficult to have more stable inter-spacecraft separations. They can, synchronizing the period a little more tightly would make all of these trend lines much flatter, and there would be less drift between the satellites. And the satellites are low thrust, so we know that they can achieve kind of precise maneuvers. And so, to me, this seems like, this is, again, speculation because I don't have insight into their operations, but it seems like a conscious choice to let them kind of bang around within this rough plus or minus 40 kilometer box. So the question becomes, why? Is that driven by CA and just kind of wanting some extra wiggle room for moving around at plane conjunctions, or what? Certainly doesn't seem like it would be beneficial towards ground coverage. So it's, I think, an interesting result, but it's kind of unclear what the actual motivation is. But I would argue that letting them bounce around like this is kind of a conscious choice. So given that look at their separations within the mission orbit and seemingly that they're maneuvering a lot, what does their CA look like? And so, I know this plot kind of looks freaky in a lot of ways and kind of scary, but I'll go ahead and kind of explain it. So what I did was, for a given day's TLE set, take those TLEs and propagate them for 7 days and just screen everything at the mission altitude against each other. And then take that and do it multiple days over, day over day over day, to just kind of see what's going on. And what you can see is that over the first couple of days, it's kind of light, and it's, I'm looking at everything up to, conjunctions of 50 kilometers, which I can guarantee you they're not worried about 50-kilometer separations, given the size of the constellation, and the fact that they have precise GPS solutions. They're not going to need to worry about 50-kilometer separations. I'm sure they're only worried about the closer conjunctions, and to be perfectly honest, I don't even know what level they would be worried about. I certainly would be worried at anything below. I'd want to track anything below 5 kilometers, but I don't know what their tolerance for closeness and risk is. The risk ultimately will be driven by the covariance of the satellites, which, as I said, will be good, especially for the first few days. You can see when you trend these over time, while there's changes, there are some kind of consistent trends. And what I mean is, it seems like the first 3 days or so are usually not too bad, especially in terms of closer conjunctions. And it's not until after about 3 days that you start seeing this kind of deluge or, tidal wave or, sandstorm, whatever you want to call it. Kind of looks like both to me, of conjunctions over time. And so, it's given that they seem to be maneuvering, kind of on average every few days, is that part of the driver that, kind of pushing things off into the distance as you have kind of closer, smaller conjunctions in the near term? Do you maneuver and then, just kind of worry about later? That seems to be kind of what they're doing. They have this, kind of much publicized automatic, maneuver planning or onboard maneuver planning system where they just kind of upload their data and the spacecraft perform their maneuvers. So, perhaps that onboard maneuvering is what's driving this kind of continual, like, 3-day lookout of kind of a lot of conjunctions coming down the pipe. It's hard to say. Like I said, I don't know their operations, but this is what the data appears to show. Another thing I'll note is that I color coded all these by the latitude of crossing, because that's a convenient way, at least in my mind, to look at. There's so much data, you got to find some way to kind of separate it out. And at least with the latitude of the conjunction, you can identify kind of deterministically what the RAM separation of the two planes of the conjuncting spacecraft are. For instance, if the have the note at the bottom for the latitude of 0 degrees, at an equatorial crossing, which is indicated by 0.04 here as kind of the average. At that crossing, it's two counter-rotating planes that are separated by 180 degrees in RAN, and basically the higher the absolute value of latitude, the less and less separation you have between the planes in delta RAN. So the plane that's got a delta RAN of 10 degrees with its nearest neighbor plane, that has a conjunction that's at the upper reaches of the orbit, at a latitude of 50 or 51 or 52 degrees. And so the nature of those conjunctions is significantly different. You have satellites kind of coming up alongside rather than these kind of head-on conjunctions like you have more so at or kind of crosswise conjunctions you have at the lower latitudes. And so, yeah, you can see that there just seems to be just a lot here but it's kind of always 3 days away, seemingly. But if another way to look at it is the actual radial separation, because if you have a kilometer, 2 kilometers of radial separation, even if your conjunction is only 2 kilometers, that's going to be very safe, especially with GPS quality OD solutions. And so, what does the radial separation for all these conjunctions look like? And it stands to reason. They're keeping SMA fairly tight, and so all their conjunctions are in the kind of 1 to 2 kilometer. If outliers of 3 and 4, but they're in kind of the 1 to 2 kilometer separation range. And so I would argue really anything over a kilometer on this plot is arguably very safe and doesn't require much additional analysis. But looking at the radial, you also end up seeing kind of an interesting artifact associated with planes being inserted. And when you look at day 317 so 316, everything's kind of within a couple of kilometers radially, and then 317, 318. You get these kind of big trends, very kind of linear trends, and then 318 or 319, they're gone again. And what happened is over days 317 and 318, plane number 55 was inserted into its slot in the mission orbit. And so this is the absolute value of the radial separation. So what you see are, at the farthest left, you see the planes kind of coming up from underneath. And then the TLEs were fit to kind of those last few maneuvers as they were ascending. So the TLE fit propagated out over time shows a continuing ascent that, actually never really happened. So none of these conjunctions were ever really going to happen, but it provides a very easy indicator, even if you were just looking at CA data, of when, satellites were entering the mission orbit. And so you can see as, they kind of get more initialized, the slope goes down, and then eventually they're gone as they've circularized into the mission orbit. As I said, there's been a lot of conjunctions, but based on the quality of their GPS solutions, there probably a lot of these they're not worried about. So the question is, what are they worried about? Is there any way to figure out what they're worried about? So to do that, I have kind of a case study example that I found when just kind of looking through the data. So what I did was I took all of the, for a given, set of days data, I just labeled with the satellite IDs any conjunction below a kilometer. And as I just kind of went through day to day, I saw basically things like this where there were a handful. But then I ran across this day 315, which was, just a week or so ago, where I noticed that satellite 1309, it's, circled in all the conjunctions are circled here, had 4 different conjunctions under a kilometer in the space of, 2 days, and 3 days worth of prediction. And 2 of those conjunctions were actually below 250 meters of separation. And one of these, I think it was the first one with 1354, actually the radial separation was only 30 meters. Now, it's important to note that while I think the TLEs are pretty good, they are not, 100% accurate. So I'm sure that there were probably 4 very close conjunctions. I don't know. I can't say that it was exactly 30 meters. Maybe it was 50, maybe it was 75, maybe it was 100. But there were 4 close conjunctions that were predicted on day 315 to happen in a couple of days. So, in my mind, that is absolutely something I would want to mitigate, and I would do something about. I would maneuver 1309. So I looked at the plane that 1309 was a part of. I looked at its inter-spacecraft separations, and sure enough, something happened. It's hard to say what, but if you look, this is the same plot of inter-spacecraft separations. This is for plane number 63. It's at a larger scale because you can see that, so these purple and gray outlier lines are the separations of 1309 with the spacecraft ahead and behind. And you can see that actually prior to 1315, it was kind of out of box already. I don't really have insight into what that was, but between 1315, when the conjunctions were first predicted, and 1318, kind of after the time period of those conjunctions, it goes way outside of the nominal box. It had a large jump in semi-major axis and a long track separation that was then consistent for multiple days and trending the same way. And then it went back. This line is actually, as I indicate here, a bad TLE feed. I went back and confirmed that the RMS value of that particular TLE feed was 9 kilometers. So it was very erroneous. Probably driven by whatever maneuvering it took to get the satellite back into its slot, because for the remainder of this period, it was back in its slot. So clearly something happened to satellite 1309 over this time period. It's really hard to say, whether or not it was a mitigation maneuver, but it kind of appears to be, to me, because if you then go back and look at the predictions from subsequent days, what you see is a different, prediction of conjunctions from 1309. There are these first two that are low are there, but they've essentially, this is a prediction from a day later. So even though they're happening kind of roughly the same time, they've been pushed out another calendar day, and they're not as bad. There's fewer of them. They're not as bad. And then actually with the subsequent prediction the next day, there were no longer any 1309 conjunction predictions. So, while I don't have a smoking gun, this is pretty close, I think. It certainly seems like something happened. And so the real question is, if I kind of closely parse through all the close conjunctions I can find in the data, how often are these maneuvers happening? I suspect fairly often. I only had to look through a few days of data to find, a four satellite conjunction, or 4 conjunctions for one satellite. So I suspect there's kind of a lot in the data. For the most time, I've been kind of just looking at it in aggregate. But so that's kind of the majority of my talk. As I said, I did all the analysis in FreeFlyer, and I think I was able to figure out a decent amount. They're operating at kind of a near frozen that they're holding manually. Their ascents take anywhere from 50 to 150 days. They raise SMA by about 6 to 10 kilometers per day. Their ascent from parking up to mission orbit takes about 25 days. They've got enough satellites launched to get to half the constellation. They're at about 34% right now. And I would love to peek into their operations center to get a feel for staffing and automation, because they are just doing lots and lots of maneuvers. There are many times when they're maneuvering hundreds at a time, and those are orbit raising and orbit lowering maneuvers. Doesn't even count for the SKs or conjunction avoidance maneuvers, which you can see seemingly happen a lot. And it's hard to say exactly how they're handling CA. I think they're having to maneuver for interconstellation conjunctions, but it's hard to say how often or to what degree. And I haven't looked at all at conjunctions with external debris. I don't know how often they're maneuvering for that. That could be also part of why they kind of slop around in their box. The final note I'll say, because I'm very much running out of time, is these are some of the features that I found very useful in my analysis. Using Brouwer-Ladane mean element sets were very helpful for providing kind of more stable element set search logic and plotting. Using structs and JSON for data organization and archival. The socket object, that's what I use to automatically download the TLEs every day. File system object was for file organization of all the TLEs and any additional data files I create. Plotting utilities, I mentioned of using the color palettes to synchronize data between views and plots, and kind of create a standardization there that help, I think, make it easier to kind of discern data. And then reference lists are very handy for kind of reorganizing your access to the data without duplicating the data or anything like that. Command line to run batch jobs. There were various times when I would change how I did the CA or additional analysis, and I could do a command line call and kind of rerun all my historical data and kind of get past data back up to current analysis standards. And then procedures. You know, if you're going to do it once, any more than once, do it as a procedure and make sure it's reusable. It makes things a lot easier.
Thanks, Michael. That was a great session. Honestly, you kept me so focused for the whole 45 minutes. Before we get to questions, I want to just tell you that slide 11, the graph that you have there, is a piece of art. And actually, the first question that we had is, were all of the plots that you're showing generated in FreeFlyer, or did you do some kind of post-processing?
No, these are all pure FreeFlyer plots. The only reason they look different is because I took advantage of the new features in 7.6 that makes it really easy to kind of fully change the plot palette, the background palette, the plot, you know, fonts and themes, all that stuff. It's all stock FreeFlyer now.
Awesome. Before we get to the questions or go back to them, I just want to remind everyone we have 15 minutes. We can answer any questions you have about FreeFlyer, about Vali's work over here. So Vali, I would like you to keep your slides because I think we might have to go back to them.
Sure.
Which tranche did you select for plane one? Can you go back to that?
Sure. So I'll kind of flip back and forth between these. So what I used as plane one, you know, was launch two, the first launch of the quote unquote operational satellites. You know, this a launch from 2019 or from early 2019 was the quote unquote 0.9 satellites that they only went up to 530 kilometers. And so they were never really operational. And then, as I said, they deorbited most of them. So then the launch from late, I think it was November 2014, or 2019, sorry, excuse me, was the first launch of operational satellites that they put into mission orbit. So so I used that as my kind of anchor point, and plane number one was the first plane to make it to the mission orbit. So everything else is just delta from there, and you can see they're keeping fairly regular, you know, RAM separations from that initial plane.
Yeah, that's pretty clear. And you mentioned earlier when you first started that all of these graphs that you're showing, all of the colors are consistent, right? So over here, the red here, every other slide that you showed with the results, the red stands for the same plane, right?
Yeah, mostly. Not everyone. There were, like, when I colored by latitude, that didn't have anything to do with launch. But yeah, you know, anything that I tried to have you know, some traceability back to the original launch, use the same color scheme. So, you know, there's slight differences in the tone based on the plotting versus the view, but orange is orange and the like.
Yeah.
So.
Okay. So how did FreeFlyer handle propagation of so many spacecraft?
That's a good question. Well, you know, most of the time, when I did propagation, you know, I did TLE based propagation, which is fairly fast. But what I do, you know, a lot of times is just parallelize based on, you know, number of planes or something like that. It's very easy. And that's also why I mentioned, you know, using JSON and command line is it's very easy to kind of whip up a JSON struct that's your input for a run that says, you know, just propagate, you know, planes 3, 4, 5, and 6, you know, on one process in FreeFlyer, and then kick off a different process in FreeFlyer and run planes 7, 12, 14, and 18. So I parallelized when I could, or really when I needed to. But all the work is done just on my laptop. I didn't farm it out to the cloud or any like compute cluster or anything like that.
Yeah. Okay. And I believe we're going to talk about this more at the end of today, right? During Mark's session as well.
A little bit, yeah.
Yeah. We got a few more for you. Can FreeFlyer detect maneuvers from TLEs, or do you have to perform a manual analysis as you showed in slide number 11? In case it can, what's the minimum size maneuver it can detect?
So there's not really an automated way to detect conjunctions in FreeFlyer. A lot of people that kind of trend TLEs to try and look for maneuvers tend to really just look at semi-major axis and period to look for discontinuities in those and say, oh, a maneuver happened. One of the things about maneuver detection that's very difficult is it's really a function of the size of the maneuver and really kind of the size of a thrust. And so for low thrust missions like Starlink, it becomes very, very difficult. It's just, when, if they just do a 30-minute, I don't know the exact size of their propulsion system. It seems like they can deliver as much as 10 kilometers of SMA change a day. But I don't know, what fraction of the day that's burning and whatnot. But for smaller burns that, maneuver detection gets harder, especially when you have some amount, even with good TLEs, there's some amount of noise associated with good TLEs, and it makes it difficult. So I had to really kind of drive the maneuver detection really just based on the kind of finest level of detail I could reliably get to, which to me seemed to be the in-plane separations.
Yeah, that makes perfect sense. Thank you, Michael. So a few more for you, and we have some comments that we would like to share as well. Were the conjunctions strictly close range calculations, or were the PC values calculated using FreeFlyer's built-in methods?
Sure. Yeah, that's an excellent question. I did not do P sub C calculations. That certainly would be a logical extension of this current analysis. But part of the reason I didn't do it is one, I don't have direct knowledge of the covariance that these satellites have. I can certainly make approximations. As I said, it's known that they have pretty good GPS solutions. How good is good, I don't know. So any P sub C calc would really be an approximation based on a guess of what the TLE, or I mean it's further complicated by TLEs, but it'd really be a guess on what the definitive covariance prediction is. And then you throw on the fact that maneuvers may be happening. That just makes covariance prediction even harder. So it would be very difficult, and it would be very, very speculative to do P sub C calcs. I don't know how reliable they would be, but it would be interesting to check it out, certainly.
I bet. Of course. So what was the most difficult part of your analysis from all of what you worked? And following that, what are you planning to do next?
I mean, I would say really the hardest thing was just sifting through all the data, trying to figure out what was something important and what was something that wasn't. The things like the ascent plan and stuff like that was, basically you just kind of have to look at the data over time. And so, to really kind of be able to figure it out. But when it comes to maneuvers and CA, it was really trying to figure out how to slice and dice the data. I mean, the whole reason I started this analysis was, essentially SpaceX is providing a lot of data, but they're not really providing a lot of information. They've talked about their onboard maneuver planning and and their FCC filings, and they claim that they have no conjunction risk, but and they're letting these TLEs out through Celestrak, but there's not much information about their actual operations. I mean, they start these large maneuver plans, and I think they make notice to NASA entities and probably the Air Force, but they're not exactly saying, hey, greater world, we're maneuvering 180 spacecraft today. So it was kind of a lot of data, but not a lot of information was kind of what prompted me to do this, was trying to figure out what knowledge could be gained.
Yeah, and honestly, on behalf of everyone, I think we all appreciate that analysis. So I have a question for you. You looked at Constellation CA. Why didn't you look at other kinds of CA as well? You know, debris or other spacecraft. Do you think that's the most important, or why?
Sure. Yeah, that's obviously a very, very relevant and very pertinent question. So part of the reason I did it was because one, the interconstellation has more of an operations bearing because, it's a product of how they've structured their constellation as much as how they and how they operate their constellation as anything. And so looking at intra-constellation CA, I thought kind of gave more of an insight into their operations, which I was very curious about. And secondly, there seemed to be kind of less information about that. SpaceX really is just kind of in their SpaceX or in their FCC filings have said, well, we've got our automated maneuvers, we've shown that, conjunction risk is very minimal. But that's kind of been the extent of the depth of the answer. And I wanted to plumb the depths a little bit more and figure out more. And there's more public analysis and public information with regard to external conjunctions. People have used Socrates to do Starlink versus debris conjunction analysis, and so I wanted to look at their, what kind of showed more of their operations philosophy, if you want to call it that.
Okay, yeah, I appreciate that. So we have a comment from, and it says, relative separation trending was an excellent way to detect small maneuvers. So thumbs up, Michael. All right, so we have one question. We have time for two more questions. We got one just came in. So take another one afterwards. What type of information could be released by a constellation operator that would assist observers in analysis like this? What would be better information rather than data?
Yeah, that's a good question. I mean, I think, certainly, any sort of kind of forewarning of large maneuver campaigns, to kind of suddenly, raise the orbit of, 180 satellites by 30 kilometers, make sure to let, anybody, relevant know. And, I don't know what the right venue for publishing that data would be, but I think certainly large maneuver campaigns would be helpful. I don't know, maybe, actually publishing full EFEMs rather than TLEs. I don't know. I guess I would have to think about it a bit more, but certainly maneuver information. Even just back of the envelope covariance information would be helpful too. Because then you could at least kind of ballpark, P sub C calculations without it being so back of the envelope and so speculative. That certainly would be helpful, but it's understandable if operators wouldn't want to do that for sure.
Okay,
that's the best I can think of off the top of my head.